our honor to introduce our project, Coffee Whisper, Metal Wire Formation Machine with IoT. Introduction. When we learned about the wire formation machine for the first time in our mechanical manufacturing class, we were all fascinated by its theory and potential application. The only downside, however, is that the wire formation machines on the market now are mostly large and expensive. Eager to learn more about this incredible machine, we decided to make a wire formation machine with small in size, low in cost, and can allow users to operate with numerical control at the same time. But how can we make one such machine out of thin air? Before we put our theory into test, first of all, we use CAD drawing to make a sketch. Then we do programming coding in Python, so that the machine can convert DX CAD file into C code. After several attempts, we make our finished product.
Equipment, wire formation mechanism design and manufacturing process. Before we complete our machine, first of all, we need to make the wire formation mechanism. Let's take a look at our mechanism design and manufacturing process. As you can see, this is our wire formation mechanism, which uses the lower stator motor to drive the upper line 14 shaft to rotate and bend the material. We deliver from the metal line guide. For our stator motor model, we choose a model 42 stator motor and increase our output torque with 1 to 5.18 planetary reduction compartment. Combine the stator motor and the line guide, we now have the wire formation mechanism. The following is the completed design figure. We want to test the deformation of the material. When the chamfer edge of our follow line guide fares the maximum force of the motor. After we validate the above calculate, we discover the maximum force to be 107.93 Newton. Then we use simulation to calculate the maximum deformation of our material to be 0.2437 micrometers, which does not have much impact on our material. Now that we have a wire formation mechanism, we will move on to make our product more realistic in terms of 3 dimensions.
ASIC rotating mechanism design. To achieve a goal, we make an ASIC rotating mechanism. Its function is to allow the wire formation mechanism to rotate and fall into a 3-dimensional shape. Screw driving mechanism. Another design that is equally important is the screw driving mechanism. It is designed to make our machine move up and down, so that we can bend anything in the negative bending angle and cut lines.
Wire cutter head design. Next, we also need to come up with a wire cutter head. This is used to cut off the 4D shape without manual cutting, which will come in handy when the machine goes into mass production. This is the mechanical drawing for our machine assembly.
Circuit configuration. To help the preliminary machine move smoothly, we turn to the Arduino and ramps of the 3D printer that we have learned before as our circuit system. Arduino parameter setup. In the above picture are the control parameters we modified to control the motor. As you can see, here is completed machine we assembled. After the assembly is completed, we can now try folding out the product the way we decided.
Experimental result. Wire formation experiment with different wire folding pin diameters. In order to find the best condition to make perfect product, we spent months conducting numerous experiments. During the process, we repeatedly use wire folding pin of different diameter to match with line guides of the same diameters. We found that the bending angle are almost the same.
wire formation experiment with different line guides. We use line guides of different sizes with metal wire of the same diameter to carry out our experiment. We find that the smaller the diameter of line guide is, the smaller the folding angle of line guide is.
Experiment with wire of different materials. To find out more about the effects of wire material on the product, we collect a few different materials such as metal wire wrapping paper, copper wire, iron wire, and aluminum wire. Here are the wires we have folded. And our experiment proved that our machine can be used to fold and shape the wire of different materials into any form we design. No doubt. The machine is quite versatile as well as cost-effective.
Wire feeding mechanism positioning repeatability experiment. Next, in order to test the precision of our machine, we feed aluminum wires of the same length into the machine at the same speed. We repeat the same experiment for at least 20 times, and we find that its accuracy can reach within a range of 0.01 millimeter, which is a rather promising result. Wire feeding speed experiment. To make sure that the machine can work stably, we do more experiments in terms of different speeds from 100 to 5,300 millimeters per minute. During the process, we discovered that the machine can remain stable when the speed reaches 3,200 millimeters per minute. However, its accuracy is still within 0.01 millimeter. However, when the speed is higher, we can no longer acquire the same precision.
Trim point positioning experiment. We conduct this experiment in order to find the best coordinate point for the wire cutter to get a clean cut. This way, we can prevent accidents from happening. To achieve this goal, we have to get a way in which the machine will create the smallest burr when cutting wire. At the end, we find that we have get a perfect edge when the G code is set at 45.
Software. Below is the setting for the wire length and the direction of angle bending in our program coding. In order to get right result, we conduct many experiments and repeatedly correct the errors between the actual bending angle and the set value of x-axis. The formula has been used to calculate the line length L, vector dot product calculation angle, vector cross product to determine the direction of bending angle to be clockwise or counterclockwise. This is a program interface that we develop. Users simply have to save the join cat join as a DXF files and then import it into our program so that the machine can read the bending code. Here is a comparison of our finished product and CAD files.
IoT. Next, come to the part of our addressable Internet of Things. IoT. At first, we had three choices. Not knowing what to do, we consult our teacher and develop our comparison. At last, we came to an agreement and decided on ESP01.
Conclusion. Overall, our machine has a graphical function. Also, by using Python to write DXF code, we can easily convert code into G code. Therefore, the operation is simple and straightforward. On top of that, our machine enables users to fold out the three-dimensional model. What's best, since we are all high school students, we made all the machine parts from the ground up on our own, which means the cost is relatively low. That's all. Thank you.